Hi, this is Kanakambika from Department of Mathematics. Now I present some few concepts in real analysis. Let us start with functions. Before going to the functions, let us see some basic definitions. Let us start with set. Set is nothing but it is a collection of well-defined objects. Examples of set is vowels in alphabet is a set. Similarly, the even numbers between 1 to 10 and odd numbers between 1 to 10 etc. are the examples of set. We can have many examples in day-to-day life also. The trees in a particular park is an example of set. Similarly, we can say that the number of students in a classroom is also a set. In functions, let us consider two sets A and B. Function is nothing but there exists a relation between A and B. Suppose the each element x of A is associated with an element of B in some manner. It is denoted by f of x. Then f is said to be a function from A to B or mapping from A into B. The set A is called the domain of f and the elements of f of x are called the values of f. F of x belongs to the set B. The set of values of f is called the range of f. Let us see an example for a function. Every situation in our life can be created as a function. Let us see a growth of a plant in a particular year. If a tree grows 20 centimeter every year, then the height is related to a age. Here the relation is the age and the height of the tree. Therefore, the function is f of age and the f of age will be equal to age into 20. Suppose age equal to 10 years, then f of 10 will be equal to 200 centimeter. Similarly, we can find it for any years. So, this is a generalized function. It can be converted as a mathematical equation such as here x is considered as age and the height is considered as f of x. Then the f of x equal to 20x. For each value of x, we can find the value of f of x. Likewise, we can create every situations or any relations can be a function. Let us see an example for domain and codomain. Here the function is f of x equal to 2x plus 1. A is a set and B is another set. A is considered as domain and B is considered as codomain. The elements in A are 1, 2, 3, 4 and the elements in codomain are 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Here the relation between the domain and codomain is 2x plus 1. First element 1 is related to the element 3, that is 1 into 1 plus 1 is equal to 3. Similarly, the second element in A is related to the element B 5. Similarly, the third element 3 is related to 7 in B. The fourth element is related to 9 in the set B. The values 3, 5, 7 and 9 are called the range of that function. Always range is a subset of a codomain and it may be equal. Let us consider the two sets A and B and F be a mapping of A into B. If E is a subset of A, then f of E is defined to be the set of all elements f of x for x belongs to E. F of E is the image of E under the function f. F of A is the range of f. It is clear that f of A is a subset of B. That is, the values will be in B. That is, range is a subset of codomain. In some cases, the range will be equal to codomain. Let it is called as onto function. Let A and B be two functions. Let f be a mapping of A into B. If f of A equal to B, that is, the range of a function is equal to the codomain, then we call this function as an onto function. Next one is one-to-one function. Let A and B be the two sets and f be a mapping from A to B. If E is a subset of B, that is, now we are considering the codomain, then f inverse of E denotes the set of all x which belongs to A. Here it consists the elements in domain such that f of x belongs to E. Then f inverse of E is the inverse image of E under f. If y is a subset of B, f inverse of y is the set of all x belongs to A such that f of x equal to y. If for each y belongs to B, f inverse of y consists of at most one element of A, then it is said to be the one-to-one mapping of A into B. It is the traditional definition for one-to-one mapping. This can be also expressed in the following way, that is, if there exists a one-to-one mapping from A to B, it must satisfy the condition f of x1 not equal to f of x2 whenever x1 not equal to x2, where x1 and x2 belongs to A and f of x1 and f of x2 belongs to B. Instead of satisfying the above conditions, if this condition is satisfied, it is called as one-to-one function. For proving a one-to-one function, it is enough to prove a one-to-one correspondence between the set A and B. If there exists a one-to-one mapping of A onto B, we say that A and B can be put in one-to-one correspondence. Or it can be stated that A and have the same cardinal number, or crisply it can be called as A and B are equivalent, and it is denoted by A equivalent to B. But traditionally, to prove the equivalent, it must satisfy the following three properties, that is, A must be reflexive, A must be symmetric, and A must be transitive. Any relation which satisfies the above three properties is called as an equivalence relation. But simply we can say that if any relation function which satisfies the one-to-one correspondence is also an onto function. Next, finite, countable and uncountable set. For any positive integer n, let Jn be the set of elements whose are integers from 1 to n. Let J be the set consisting of all positive integers. So J is also an infinite function. For any set A, we have to prove that A is finite. Nothing was given, simply it was given as A is a set. So, it is enough to prove that there exists a one-to-one correspondence between A and a finite set. We can say that A is finite. Here, Jn is a finite set. Therefore, if we prove that A is equivalent to Jn, that is, there exists a one-to-one correspondence between A and Jn, we can say that A is finite. The empty set is also considered to be finite. Suppose if you want to prove A is infinite, it is enough to prove that it is not a finite set. Then if we want to prove that A is countable, it is enough to prove that A is equivalent to J, because J is the set of all integers which is countable set. Then if there exists an one-to-one correspondence between A and a countable set, then we can say that A is countable. To prove A is uncountable, it is enough to prove that A is not finite and not countable. We can say that the set A is at most countable if A is finite or countable. Countable sets are sometimes called as enumerable or denumerable. Consider two finite set A and B. We say that A and B are equivalent if and only if it contains the same number of elements. For infinite set, the idea was very vague. For proving for infinite set, we can use this one-to-one correspondence. The basic concept of proving that transitivity, equality, etc. will be very difficult. The one-to-one correspondence will give clear clarity. For proving this, let us consider this example. Let A be the set of all integers, and we are going to prove that A is countable. Consider the following arrangement of the sets A and J. A is nothing but 0, 1, minus 1, 2, minus 2, 3, minus 3, that is set of all integers. J equal to 1, 2, 3, 4, etc. that is natural numbers. We are going to write an relation between J and A which will create one-to-one correspondence from J to A. Here J is a subset of A and it is an infinite set. We are going to create an one-to-one correspondence by using the function f of n equal to n by 2 whenever n is even, and f of n equal to minus n minus 1 by 2 if n is odd. Remark: a finite set cannot be equivalent to one of its proper subsets. For example, finite set means it consists of alphabets from A, B, C, D, and its proper subset will be definitely A, B, C or any three elements which cannot be equivalent to the power set. But in the case of infinite set, it is possible. In the previous example, we have considered that J is an infinite subset of A, and we have arrived at one-to-one correspondence between J and A by using the function. So A is infinite. We can prove that if there exists an proper subset for A, then we can call A is an infinite set. The basic concept is instead of satisfying all the three property, we can say that if there exists a one-to-one correspondence between two sets, then they are existent one-to-one mapping. Thank you.